Let us look at an application of the Banach-Steinhaus's theorem. Now we are going to prove the existence of a continuous function whose Fourier series diverges at the origin. We shall use the Banach-Steinhaus theorem to prove this result. Well, the Banach-Steinhaus's theorem is basically a corollary of the Baire category theorem. So it is a Baire category theorem which is doing the work of proving the existence of a continuous function whose Fourier series diverges at the origin. But not only do these things exist, they will exist in plentiful. Now let us take a 2-pi periodic function and let us take the Fourier series and its nth partial sum of the Fourier series. So Sn fx is integral minus pi to pi f of t into dn x minus t dt. Remember that in first module we already found an expression for the nth partial sum of a Fourier series as an integral. It is expressed in terms of the Dirichlet kernel dn chi. What is the Dirichlet kernel dn chi? You must go back and review the Dirichlet kernel and how we arrived at this formula. But presently in the next few slides you will explicitly see the Dirichlet kernel. So right now I shall not spell it out. Now we shall show that there are continuous functions for which Sn f comma 0 fails to converge as n tends to infinity. Not only for a specific f but for a large class of functions in per minus pi pi. So what is Sn of f comma 0? You have to put x equal to 0 in the integral that you see. Remember that the Dirichlet kernel is an even function. So you can remove the minus sign and let us write for simplicity Sn of f comma 0 to be Tnf. Let us just abbreviate Sn of f comma 0 to be Tnf because we can see that this Sn is linear in f. Sn of f plus gx is Sn fx plus Sn gx. Sn of lambda fx equal to lambda times Sn fx. So since Sn is linear in f, we should abbreviate it to Tn of f. And we have that Tnf equal to integral minus pi to pi f of t dnt dt. Now suppose we assume that the Fourier series of every continuous function converges at the origin. We have to arrive at a contradiction. So the proof is by contradiction, which basically would mean that Tnf will converge to a number for every f. So where are we? We are saying that Sn of f comma 0, namely Tnf, converges as n tends to infinity for every function f, which means that the sequence Tnf must be bounded for each f. So now by Banach-Steinhaus's theorem, there must be a common upper bound m such that mod Tnf less than or equal to m for all functions f with norm f less than or equal to 1. In other words, the modulus of integral minus pi to pi ft dnt dt is less than or equal to m for all n. And whenever f is periodic with minus 1 less than or equal to f less than or equal to 1, we are going to work with real functions in this application. So now to carry on the discussion further, we shall need some important information concerning the absolute value of dnt integral. So the displayed equation 7.2 is important and it tells you that integral minus pi to pi mod dnt dt approximately is c times log n, where c is a universal constant, and that means that these integrals, integral minus pi to pi mod dnt dt goes to infinity as n goes to infinity. That's the important conclusion. But let us assume this for the moment. The dnt is a very specific function and we have to take the absolute value and we have to integrate it. We get a bunch of constants and these constants behave like c log n, and log n goes to infinity as n goes to infinity. This is display 7.2. We shall use this very critically. So please observe this display very carefully and docket it in your mind because we are going to use it. So now suppose in 7.1 we take f to be the signum function, a certain type of signum function which takes values plus or minus 1. So where do I want it to take the value plus 1? I wanted the function f to be plus 1 on all those intervals where d and t is positive. And I want the function f to be minus 1 on all those subintervals where dn is negative. So what happens to f of t dnt? It will simply become mod dnt. Correct? So suppose if I take such an f in 7.1, then what will we conclude? 7.1 will imply integral minus pi to pi mod dnt dt will be less than or equal to m for all n. And that will be a contradiction because 7.2 says integral mod dnt dt goes to infinity. So how can a sequence which goes to infinity be bounded? That will be a contradiction. But there's only one small technical glitch in this argument, and the technical glitch is that this function f of t that we have defined, the signum function that we have defined, is not continuous. It becomes discontinuous at each place where dn changes sign. Remember, f is 1 when dn is positive, minus 1 when dn is negative. So whenever dn has a 0, at that particular place, the signum function will be discontinuous. Whereas 7.1 is valid only for continuous functions, which are 2 pi periodic. So we are not applied 7.1 properly. It's an illegal application of 7.1. So we need to first legalize this. To legalize this, let us observe first that the d and t alternates signs in alternate intervals of length pi by n. So the dn expression, it will change sign, but the change in sign will take place over subintervals of length pi by n. And as such, this signum function that we have defined is in L1. It takes only two values, plus 1s and minus 1s, and everything is bounded. The intervals are bounded. So the function is bounded, and so it is in L1 of minus pi pi. Now we can appeal to Lusin's theorem and obtain our signum function sigma as a limit of a sequence of continuous functions on minus pi pi converging to f in L1 norm. Lusin's theorem says that every L1 function is an L1 limit of a sequence of continuous functions. So this signum function, which is in L1, can be approximated by continuous functions in L1 norm. And I can further assume that these continuous functions vanish at the two ends minus pi pi, so it has a 2 pi periodic extension. Okay, so now we have integral minus pi to pi mod fjt minus the signum function sigma t goes to 0. I denoted the signum function here by sigma t. So now integral minus pi to pi mod dnt dt, which is integral minus pi to pi dnt into sigma t dt, add and subtract an fjt, add and subtract fjt, and use triangle inequality. So we get that is less than or equal to integral minus pi to pi dnt into mod sigma t minus fjt dt plus mod integral minus pi to pi dnt fjt dt. But the second one, the second piece is less than or equal to m because of 7.1. The fjt's are continuous and they vanish at the endpoints and they have values supremum less than or equal to 1. So second piece is less than m. What about the first piece? The first piece is less than or equal to the supremum of mod dnt times integral minus pi to pi mod sigma t minus fjt dt. I have taken the supremum of dn, I have taken the supremum out. But we know exactly what is the supremum of dnt. The supremum of dnt is capital N. So we got that estimate. Now allow the j to go to infinity. allow the j to go to infinity, and the first piece, integral minus pi to pi mod sigma t minus fjt dt, goes to 0. And so we are left with integral minus pi to pi mod dnt dt less than or equal to m. That's exactly what I said. You see in the slide now. We allow the j to go to infinity, we get integral minus pi to pi mod dnt dt less than or equal to m, because integral minus pi to pi mod fjt minus sigma t dt goes to 0 as j goes to infinity. And this is a contradiction because the left hand side LHS becomes arbitrarily large. So we have finally legalized the proof by careful application of Lewsen's theorem. Now what remains is to prove the equality 7.2. Integral minus pi to pi mod dnt dt. This integral is denoted by ln. These are called Lebesgue constants. The sequence of constants is called Lebesgue constants. A great deal of information has been unearthed about the asymptotic behavior of these Lebesgue constants. There are many research papers have been written on this, but we shall not be concerned with those delicate points of analysis concerning these Lebesgue constants. We'll only need this very coarse estimate that this number ln is approximately c by this number ln is approximately c log n, and when n goes to infinity, this goes to infinity. This is all that we really need. So now, because the dn is an even function, it clearly suffices to look at the integral from 0 to pi. Here you see the explicit formula for the Dirichlet kernel. What I had promised that you will actually see the Dirichlet kernel being displayed in the next few slides, I said, and here it is. And where does it change sign? It changes sign at the points k pi by n plus half, k equal to 0, 1, 2, 3. The denominator doesn't change sign at all. Remember that t runs from 0 to pi, so t by 2 will run from 0 to pi by 2. So sin t by 2 in the denominator is going to be positive. So denominator doesn't change sign, this numerator changes sign at k pi by n plus half, k is a natural number, and these points at which the dnt flips sign, it subdivides the interval 0 to pi into subintervals, each of length pi by n plus half. So you got a bunch of subintervals. Remember that 0 less than or equal to x less than or equal to pi by 2, sin x less than or equal to x. So 1 upon sin x is going to be greater than or equal to 1 upon x. So 1 upon sin t by 2 is greater than or equal to 2 upon t. So what do we have? We have that mod dnt is going to be greater than or equal to 2 upon t mod sin t into n plus half. Now let us take a subinterval, one of these subintervals of length pi by 2 into n plus 1, n plus half. So let us display this interval ik explicitly. The ik you see in the middle of the slide displayed, ik equal to set of all t, which lies between pi times k plus 1/4 upon n plus half and pi times k plus 3/4 upon n plus half. Look at this interval ik. This is a smaller interval. I had taken each interval, each of the original intervals on which dnt maintains the positive sign or maintains the negative sign, and I had taken a slightly smaller subinterval. I had cut out the two ends. So on these, when I cut out the two ends, what happens to mod sin t into n plus half? It's like this. The sine function goes from 0, it takes the value 1 at pi by 2 and again comes down to pi. So at the ends of the interval 0 to pi, the sine function is small, but the middle part, the sine function is large. So now we have to look at what happens to sine of t into n plus half. Everything gets scaled by n plus half, so n plus half comes in the denominator. So on the smaller interval, the sine function is bigger than 1 upon root 2. So that's what I said, mod sine t into n plus half is greater than or equal to 1 upon root 2 on this smaller interval I sub k. So mod dnt, which is greater than or equal to 1 upon t, because what happens is that you will be left with the root 2 in the denominator. And so mod dnt is going to be greater than or equal to 1 upon t. And 1 upon t is bigger than 2 upon pi into 2n plus 1 upon 4k plus 3 on this subinterval ik. So on each of these subintervals ik, I got a lower bound for d and t. So now look, integral over ik of d and t mod is going to be greater than or equal to 2 upon 4k plus 3. So this is the estimate of the integral on a smaller interval. So on the larger interval, the integral d and t is going to be still larger. So the total contribution of mod d and t over all the intervals whose union is 0 to pi is going to exceed the contribution from all these smaller intervals. Since mod d and t is non-negative, when I integrate over a smaller interval, I get a smaller number. Integral over a larger interval is going to be larger. So integral of 0 to pi mod d and t dt is going to be larger than the sum of the integrals of mod d and t over I1, I2, I3, etc. But on each ik, we got a lower estimate 2 upon 4k plus 3. So I must add up 2 upon 4k plus 3 for k equal to 0, 1, 2, 3 up to k, and I get exactly a constant times 1 plus half plus 1/3 plus etc. plus 1 upon n. But now add and subtract a log n. 1 plus half plus 1/3 plus dot 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 plus 1 upon n minus log n converges. What is the value of the limit? It's called the Euler's constant little gamma. So adding and subtracting a log n, I get a C log n term, and then I get a Euler's constant, which is an innocent constant. So it's going to be larger than or equal to C tilde log n for some constant C tilde. And this completes the argument that the integral mod d and t dt, the Lebesgue constants, go to infinity as n goes to infinity. And that completes the proof that there are continuous functions whose Fourier series diverges at the origin. It's a very important and illustrative and instructive exercise on the Banach-Steinhaus's theorem. It's a very important application to Fourier analysis that we have completed. Now we shall take up some basic facts from Hilbert spaces. So what is a Hilbert space? A Hilbert space is a vector space H endowed with an inner product, triangular bracket VW. So when you have an inner product, that inner product gives a norm. What is the norm? Norm V equal to V dot V square root. I already defined an inner product in module 2, and we already listed the properties of an inner product in module 2, where we did the mean convergence of Fourier series. So we already discussed things like the parallelogram law, the Pythagoras' theorem, and so on. And what do we need from there? That a Hilbert space is a special example of a Banach space. Every Hilbert space is a Banach space in the first place. What is the norm? The norm is basically V dot V square root, and hence the distance is simply V minus W dot with V minus W square root. And this distance is complete. This is a complete metric on H. So now we shall embark upon a deeper study of Hilbert spaces. So vectors V and W in a Hilbert space are said to be perpendicular or orthogonal, denoted by V perp W if the inner product of V and W is 0. Obviously, it's a symmetric relation. If V is perpendicular to W, if and only if W is perpendicular to V. So the relation is clearly symmetric. 0 is orthogonal to everything. The 0 vector is orthogonal to every vector V. Suppose I take a vector subspace. Take a vector subspace V, and we define the orthocomplement of V, and we denote it by V superscript perp, called the V perp, the orthocomplement of V. The V perp is the set of all vectors in H such that x dot V equal to 0 for all V in V. So check that V perp is a vector subspace of H. So V is a vector subspace, V perp is also a vector subspace. What is the intersection? Intersection is going to be the 0 space. Why is the intersection the 0 space? Suppose X is in the intersection of V and V perp. Because X is in V, it must be orthogonal to everything in V-perp. But x is also in V-perp, so x must be orthogonal to itself. So x dot x must be 0. That means the norm x squared must be 0, so x must be compulsorily 0. So V intersect V-perp is exactly the 0 vector. The 0 vector is orthogonal to everything, so 0 perp is V. Now, if a vector is orthogonal to everything, if x dot V equal to 0 for all V, then in particular x dot x must be 0. X must be 0. The only vector which is orthogonal to everything is the 0 vector. So, in other words, V perp is 0 if V is the whole space. V perp is 0 if V is the whole space, that is H perp is 0. Show that W perp is always a closed subspace of H. Show that W perp is always a closed subspace of H. And in particular, V perp must be V bar. So, if I take a vector subspace V and if I take its perp and take its second perp, I'm going to recover my V but with a bar on it. Now, as it happens in linear algebra, if I take a bunch of non-zero orthogonal vectors, it is automatically linearly independent. Any set of non-zero orthogonal vectors is automatically going to be linearly independent. Finally, you will also need to recall the important concept of Gram-Schmidt orthonormalization process from linear algebra. So, when I give you a set of vectors v1, v2, vk, how do you orthonormalize it? That's a procedure is called the Gram-Schmidt's process in linear algebra. It is a very easy concept and I'd like you to recall that. We will need that in the future. So, these are the basic properties of the inner product which has been summed up in this slide, a number of easy exercises. So, now in the context of Hilbert spaces and in fact in Banach spaces, there is this notion of Hamel basis. Now, Banach space is an example of a vector space. So, first and foremost, it has a basis in the sense of linear algebra, and the basis in the sense of linear algebra is called a Hamel basis. So, whenever I use the word basis without the word Hamel, it means something very different. The Hamel basis is very rarely used in functional analysis. It has hardly any use. In fact, we will never use it. So, the Hamel basis is not useful. So, whenever you talk about basis, we are not referring to Hamel basis. Definitely not. So, it has a different meaning. So, we are going to give it a meaning in the context of Hilbert spaces. So, a basis in a Hilbert space is first and foremost a linearly independent subset B with one additional property. You take the linear span of B and you take its closure, then you get the whole space H. Take a linearly independent subset B. If the closure happens to be the whole space, then you call it a basis. In linear algebra, what you do is you take a linearly independent set, take its linear span, and you don't take the closure. That's the difference. Without taking the closure, if you get the whole space, then you will call it a basis in linear algebra. Or a Hamel basis is a linearly independent subset of H whose linear span is H. But without the adjective Hamel, if we call something a basis, then it must be linearly independent and the closure of its linear span must be the whole space. We'll continue this next time.